All right. So, hey everyone. Welcome to the Cloud Native and Platform Engineering Meetup. I'm Ahmed, and as Chris said, I'm a, am I in the frame?
Yeah.
Sweet as. Yeah, so I am a Microsoft Azure MVP, and what that basically means is as like an award for people sharing content around Microsoft Azure. I'm a cloud solution architect, consultant, content creator, whatever. And I do put content on my blog. It's IA Max, and then on my YouTube channel, and this is my Twitter handle. And we actually have a clicker, which is super cool. Yeah. And I forgot to say, of course, I used to be a network architect for like 10 years of my life. So I worked for the good, when I first graduated from uni, 2005, back in Baghdad, Iraq, for telecom companies. So at that time, right after 2003, we were like just building telecom everywhere in the country. And I was really fortunate to be one of the first people to be part of that. So basically, you start with 4, 5 Cisco routers, and then you end up with 60, 70 routers, and you learn that quite quickly is that whatever technology you're using doesn't scale, so you need to learn quickly on your feet. So yeah, so basically what I'm trying to say is that spent a good time of my life before jumping into the world of cloud computing and Kubernetes, doing a lot of networking, and of course that Cillium, and I'll talk more about what Cillium is, and the whole networking is a very big passion of mine, so I'd love to learn more about that technology. So what basically I'll be talking about today is how to do networking using a technology called CNI Plugin, and Cillium is just one of the Cloud Native projects, Cloud Native Foundation project. There's a lot other CNI, but I like Cillium the most, and I'll talk more about the reasons. Yeah, so actually before I jump into what Cillium is and before I talk about the CNI, I thought that I needed to first set some ground rules about, and of course feel free to stop me at any time and ask questions. You don't have to wait for me to finish. So the first thing that I want to talk about here is that what actually was striking for me when I first jumped into the world of, sorry, are you able to see it? Or?
That's good.
Okay, good. Yeah, so the first thing is that I was surprised that actually Kubernetes does not do networking by default. And I was like, that's very interesting. So they actually created something called container network interface specification. And then what that basically means is that they offloaded the job of networking to other projects. And they call those projects a plugin. So basically, the specification of Kubernetes is all about orchestration and efficiently running your containers. But for the networking, they offloaded that to the CNI specification. So that basically means that if you want to have any type of connectivity between within your Kubernetes cluster, outside of the cluster, you need to use a CNI. By default, a lot of cloud providers provide you with the CNI out of the box. Azure, AWS, Google, they have their own default, and I'm pretty sure all proprietary CNI plugins. And then, of course, the on-premises are like even Kubernetes in Docker. And by the way, if you spot any mistake, please tell me. If you think that if there's something wrong here, please stop me and say maybe that's not right. And yeah, so for any networking, you need a CNI plugin. The other thing that I found interesting is that within Kubernetes, the pod is the basic communication model. So like when we are talking about CNI plugins and when talking about networking, it's all about a pod talking to another pod. So there is the node, which is the virtual machine where you run your pods on top of. they don't care about that. It's not they don't care, it's the responsibility of the cloud and the platform provider. If it's a Azure, AWS, or Google, they should be providing you with the underlying networking. So that's outside of the concern of any CNI. And then there is the concept of a flat or non-hierarchical network. And in a second, I'll show you this diagram to explain more about what I just said to drive the point home. But I'm just trying to give you an idea of what the networking model within Kubernetes is. So what I mean by a flat and non-hierarchical network is that basically every pod within your cluster have an IP from the same virtual network. So every pod should be able to talk to every other pod directly. So normally when you have a network, you have some devices part of a network, and then other devices part of, say, like a marketing network, and then HR network. And then those guys, if they want to talk to each other, they go through firewall, router, whatever we call them. This is a hierarchical type of networking. Within the cluster, so that developers and people, operation people, when they want to build on top of Kubernetes, the idea is that they don't need to care about this. Your pod is, as soon as you have your pod in the cluster, it should be able to talk to any other pod, okay? And then finally, no NAT. So you don't, in a CNI, you should not use any NATing because NATing complicates stuff. You are, as a cloud provider, you will be using NATing. If you want to connect multiple data centers, that's different, but within the cluster, you should not be using NATing. So this is just a basic diagram to show you the ideas that I was just talking about. So basically, this is the physical network, right? And these are the nodes. And in this diagram, we have 4 pods. And these 2 pods are running on this node, and these 2 pods are running on node 1. So these 2 nodes, they could be in the same data center. They could be in different data centers. This could be on the cloud. This could be on premises. It doesn't matter. Physical networking is outside the care of a Kubernetes network or a CNI specification. This is taken care of by whoever is building that network. Okay? So whether it's Microsoft, Amazon, or Google, on premises, whoever is providing the underlying network, they take care of this. Okay? In here, we've got something called an overlay network. That's where the magic happens. So the overlay network basically is just a way of tricking, I should say, or like a way of giving the illusion to these pods that they are part of the same network. So what this overlay is doing is that all these devices here, all these pods here, as you can see here, so like this is 10.1, 10.10.10, 10.10.1.10.20.30.40, part of the same network. If we are assuming A/24, and is so like the terminology that I'm using, is it like, do you guys understand like in like a subnet, and or is it too complicated? I could explain more about that. Is that all good? Sweet. Okay. Right. So basically the illusion here is that the CNI, what it does actually behind the scene, and this is something that I learned from my telecom mold, is that it encapsulates so you've got a packet with an address and a source address, destination address, whatever it is. So what it does is that it encapsulates the packet with another packet, and that whole layer is hidden. And when you send it, say, from node 1 to node 2, you are using the outside package. So the outside package saying, So you want to send a packet from here to the US, that's the outside package. When it reaches the data center within the US, they unwrap that packet, and now they look at the address on the inside packet. That inside packet gives this pod the illusion, even though, say, that this is in New Zealand and this is in the United States, they are on the same network. All right? So that's what basically this overlay network is doing. And within the pod containers talk to each other using something called the local host, which means basically they are like two processes on the same machine. They just talk to each other without thinking about networking. So it's almost like using the Linux networking specifications. And again, this is outside of the CNI. Is that good? Should I? Okay. All right. So the other thing that I want to talk about is a network policy. So we just started by saying that in a Kubernetes networking model, we have a permissive model. What that means is that every pod should be able to talk to every other pod. But what if you have a sensitive pod that contains some application or some database or whatever it is that you don't want every other pod to actually just easily talk to, right? That's when you start to have you need to enforce some type of security or a network policy saying like, okay, so if you are a front-end pod, you are talking to a back-end pod, it's okay, you could talk, but you could only use port TCP port 80, which basically is the HTTP protocol. That's what the network policy is doing, which is very similar if you're coming from a traditional networking world. The network policy is just similar. The difference here is that when I say cluster-wide application, so like say that you have 10, 20 pods in a cluster, right? In a networking world, in my mind, so like if trying to apply a security, you would need to apply it on a device by device. Say like, okay, this device is allowed to talk to this device. So they need a network policy per device almost. But in, sorry, I had a, yep. Yeah, so what I'm saying here is that the network policy is almost like a cluster-wide network policy. What I mean by that is that you could have one network policy to apply on all these pods. You could have multiple layers of complexity, that's okay, but you could use one network policy to rule them all. So that's the other rule. And then finally, you select a pod by using a you could use a label, you could use an IP, but basically what that means is that when you create a pod, you give it a label, and then you start to say like, okay, this pod is allowed to talk, front-end pod talk to back-end pod, and so on and so forth. That's how you enforce the policy. And then finally, the implicit deny, which basically means if I'm not specifically saying this traffic is allowed, then every other traffic is denied. And I'll show you an example policy here. So this is just a YAML file that is our network policy. So basically, that's the name of the policy. It's kind network policy, that's the name. And in here, this is the specification of the policy. So what we are saying here, we are selecting a pod with a label that is backend. So now we are telling the CNI plugin is that if you've got a pod with the label backend, this policy is going to apply to. And if the pod, if it's getting traffic, which is the ingress here, ingress is a terminology, means traffic coming in to the pod, and egress is the traffic going out of the pod. So basically what I'm saying here, we have a pod called backend, use that label. If the traffic coming into that pod, it should be allowed if it has a label of a front end, and if it is targeting TCP port 80. So that basically means that's the only traffic that's allowed. Okay? So even if the front end is sending traffic to say port 443, which is HTTPS, the secure HTTP, it's going to be blocked. That's the rule of implicit deny. So if you are not explicitly saying this traffic is allowed, every other traffic is going to be denied. Okay? What also is surprising to me is that every other pod within that cluster is not going to have anything change. They all continue talking to each other, and even this pod would be sending traffic, egress traffic, okay, normally without being affected. It's only when you apply the policy that the permissive model of all talks to all is changing and becomes what is explicitly allowed, and everything else is implicitly denied. Okay? Is that good? Any questions? Cool. All right. And yeah, so this is what we just talked about. So this, the network policy is filtering traffic between pods. So, and also the network policy could filter traffic coming into the cluster and outside of the cluster. So in the network policy, you could say, oh, I forgot to mention one other thing, is that normally in a firewall or like in even a router, when you put a network policy, you actually specify the IP. You could say like, okay, source IP, destination IP, source port, destination port, allow or deny, okay? But in Kubernetes, because the pods are ephemeral, so like they spin up and then they, so like you spin up the pod and then you kill it if the pod is no longer needed. So this IP is changing so frequently. So it's very hard for you to keep track of which pod has got which IP if you are creating a network policy. So instead, you actually match by the label. So you just say like, actually, I don't care what's the IP address of this pod. It's just matched by the label. No matter what IP it gets assigned, if it got this label, then the policy applies to it. But for external traffic, you need to have an IP. So like if you're sending traffic outside of the cluster, traffic from outside the cluster into the cluster, that's when you use IP, and the network policy does also give you the possibility, the option, sorry, I should say, to say specific IP with this specific port should be allowed to talk to the cluster. All right, so now we get to talk about eBPF. So the idea is that what I'm trying to say here, we first talked about the Kubernetes networking in general, how is it different from traditional networking. And then we talked about the network policy, which is how is it, again, different from traditional network policy, what happens behind the scenes when we are applying a network policy on a cluster. And before I could start to talk about Cillium, I need to talk about eBPF because actually behind the scenes, Cillium is built on top of eBPF. So it's the technology that is powering that's powering Cilium, and I think I'm not 100% sure, but I think it's the only CNI that's actually built from the design to use eBPF. There are other tools that actually use eBPF, and there's actually even more and more tools that are using eBPF, and I'll talk about what eBPF in a second. But Cilium is like different because it was built from the day one using eBPF. And I'm pretty sure some of the maintainers of eBPF actually work within Cilium. And Cilium is maintained by a company called Isovalent. And they've been doing a really good job and being very popular within CNI world. And they've been recently bought by Cisco, so they're doing really well for themselves. So, yeah. Right. So eBPF is actually based on an older technology called Berkeley Packet Filter. So it was just a technology to filter traffic within the kernel. So that's the magic of the eBPF. So within Linux kernel, you've got I would say a runtime. They actually filter traffic. And so what the eBPF guys came and they wanted to work and build a technology similar to eBPF, but because it was super difficult to actually change, because if each time you need to change that technology, you are playing with the source code of Linux. And as we know, the world running on Linux, and it's super hard to actually get everybody to agree on what to change. So they went in with the idea of like, okay, let's change the technology that has been used, which is BPF. They extended the functionality of it. Before it was like just basic filtering, and now they call it, it's like a lexicon or language of the runtime. It's way much more flexible now. You can match more than just basic filtering that it was. And it gave those three benefits. It's better performance, enhanced safety, and improved visibility. And the reason for that is that eBPF is actually, it's a sandbox that you run within the Linux kernel. So for the lack of a better analogy, unfortunately, I would say it's like a virtual machine. It's not a virtual machine, okay? It's a sandbox that you run within the kernel. And what that means is that it's isolated, it's safe. So before you run any program within the eBPF, there is a security check that it's not going to run forever. It needs to be secure before you actually execute the code. So that's the first thing. That's why it's improved security. Because also it's running within the kernel, it is really low overhead and very high performance because it's almost touching the hardware, right? And the other thing is that if I could show the next slide maybe. Yeah, so basically this is a slide from eBPF.io. So what provided us with is better networking security and observability. And this is what is called the user space. So the user space is where you run all your program. Whatever type of program, it's called user space. And then this is the kernel. The kernel is the software touching the hardware, right? And this is sacred. It's very hard to actually change the source code of it. So what eBPF is doing is that it's integrates into the old BPF, extended that, and whatever type of SDK you want to build on top of. So the idea is that where is the right word? Compiled to bytecode. And that is like basically the language of the hardware. But because that is really hard to program with, so you could use Rust, Go, C++, whatever language, to run what is basically called an eBPF program. And those eBPF program or application, those could be things like Falco, which is a security tool, an observability tool. It's the Cillium, the hero of our story today, and multiple other projects that actually build on top of eBPF. Right. So that basically gives us a very good idea why Cillium is really successful, is that they are using this very popular technology that is now basically allowing you to plug in and extend the kernel. So like you want to have, before it was just networking, now you could use eBPF even for storage, and a lot more technology is building on top of this eBPF because it's starting to become like a way to extend the functionality of the kernel. And I was actually so tempted to, and I was looked it up, and I was like, is WebAssembly using eBPF? And apparently it's not. A WebAssembly, Todd, right? Yeah. Todd is going to tell us more about it just now. It's basically used to just live in the web browser. It now starting to work in the server side, but there are some talks about integration between WebAssembly and eBPF. So it's really cool, and it's a very cool technology. Any questions? And so go. Right. It's a very long introduction to talk about Cillium, but I thought that was useful and helpful for us to actually understand what's the big deal about Cillium. So basically, because Cillium is Cillium is powered by eBPF. It's built on top of this new technology, and because of eBPF, it's actually really high performance and low overhead. And actually, one of the selling points on why would you want to use a tool like Cillium as opposed to just go with the native CNI that AWS, Azure, and Google guys would provide you with, is that if you're really looking for high performance, then Cillium is the way to go. And again, because of the advanced security of eBPF, and so the tool itself, the tool itself is really easy to use and really successful. It's building on, I don't want to just give all the credit to eBPF. So yes, it's building on eBPF, but they also are providing a lot more security. I listened to a talk recently with their founder, and his vision is actually Cillium everywhere. So they're thinking of having Cillium to connect multiple clouds, Cillium connecting your hybrid cloud from on-prem to the cloud, and they've been supporting a lot of technology to help them with that. So right now, for example, it's a while now they support BGP. So BGP is basically the protocol that is running the internet. Okay. So what they're trying to do is that they want to have one tool. If you have multiple environments, it's just one tool to do all your networking. Okay. And again, detailed observability, and we talked about cross-platform. Because it's using eBPF, it's actually within the kernel. So any system call, any network event, whatever type of activity that goes between the kernel to the user space, eBPF is actually able to catch it, and with low overhead. So that actually gives you really high resolution on what is going on within your environment, and you could go really fine-tune to understand all the activities within your kernel, within your networking and Kubernetes cluster. Yeah, so this is basically what I was talking about. Basically, this is, maybe it's not showing really well. This is basically the Cilium layer, okay? This is orchestration, which is Kubernetes in this case. This is the Cilium daemon. That's the bytecode injection. So whether it's a container, it's an Ethernet 0 interface, it talks to those to the containers and to the Ethernet using BPF programs. And of course, you've got the CLI, you've got your policy repo, you've got other plugins to the CNI plugin, which is ironic. And of course, you've got the Cilium monitor. You actually could get a GUI to literally plug and play your network policy to visualize what is it that you're trying to do, as opposed to just running that within creating network policies. All right. So what I'm going to do here today, it is actually applicable to any other Kubernetes cluster. In this case, I'm familiar with Azure Kubernetes, but you could run it on any other EKS, GKE, whatever other type of Kubernetes. It's called Star Wars Demo. Cilium guys created it. It's basically an idea of, so this is the idea, okay? So I'm not going to go through the analogy because maybe I'm not the most expert here. But what basically is here is that you've got two type of labels. So you've got the Death Star, which is represent a type of service that you don't want anybody to have access to. And then you've got TIE fighters and then X-Wings. So basically, the TIE fighter is part of the Empire. So you will have a policy saying like, okay, if this pod is coming from a label of the Empire, so then it's allowed to talk to the Death Star. Any other type of organization, it's not allowed. So what we'll do is that we'll create a network policy saying, basically matching traffic on from a TIE fighter to a Death Star with a TCP 80 is allowed, everything else is denied. And this is the policy. So the policy is saying that for the, in here you find the Cilium, they changed the network policy terminology. So when we said port selector, they call it endpoint selector. It's because they provide more sophisticated than the default network policy by Kubernetes. Match label org Empire and then class Death Star. That means that this policy is going to now apply on this service. If the traffic ingress coming from an endpoint with the org Empire, suite as allowed on port 80. So that basically means this guy will be allowed to talk to the this service. This one does not have the org Empire. It's going to be denied. This is what is called now a layer 4. This is a networking terminology. So in networking, you've got 7 layers. You've got the layer 1, which is cables and Ethernet and fiber cables. Layer 2, layer 3, where you have your IP addresses. Layer 4, where you have TCP UDP protocol, all the way to layer 7, where you have HTTP protocol. So this is called a layer 4 network policy. Next, we'll try to even have more security, which is even though TIE fighters are allowed to talk to Death Star, they are having the possibility, which is again just extending the analogy, is that maybe they should not be allowed to talk to the exhaust port, because that's an so you allow it on layer 4 TCP or 80 HTTP protocol, but maybe you don't want to expose all your APIs. Okay, so this API should be blocked. Only authorized resources should talk to it. So now you're going to say TCP port 80 is allowed. If you're talking to request landing, then you're allowed. Any other type of request is denied. And this is the policy for it. Basically same as the one before, just adding this method now. So again, this policy is applying to the Death Star. If you are org empire talking over port 80, you are allowed. But now you are only allowed to use the HTTP post request landing. Okay? And yeah, that's about it. And now, hopefully, the demo guides are going to work for us. So I've already prepared created a Kubernetes cluster on Azure. And I actually have everything that I said here is actually on my blog. I have 4 posts where I talk, blog post articles where I talk. Let me show you. All right. So this blog post goes deep into this is the last one, the number 4. It talks into deep details of what the concept, the details, and the method that I followed, and even the code. So if you don't have an Azure cluster, you could just build one using this Azure CLI. And then you need to have your credentials so that you could manage it using Kubernetes CLI from your command line. So I was actually doing all that before you guys joined in. So this was me creating the cluster. And yeah, so I know this is recorded. I'm not going to show all the details. Yeah. So basically what I did is that I created the Kubernetes cluster. I installed Cillium using what is called Cilium CLI. So because I'm using Mac, to install the Cilium CLI, you just say brew install Cilium CLI and installs it for you. And so basically, if we say,
can you increase the font size?
Yep, sorry. So I don't know how to do that. So wait a second. Let me see if it's Command plus, maybe. Yep. Is it good? Yep, just a second. Is it good now? Yeah. So basically, this is this just tells us that Cilium is running, and if you say yeah, so this is our cluster. It's just one node. It doesn't need to be more. It's just a node that I spin up on Azure. And what I'm going to do now is the first thing I'm going to do is actually install the application, or like provision the application on the cluster. Actually, I think I've already done that, but for the code for that is so the code for that is on GitHub, and it is part of the it's a Cilium application, so it's part of their Cilium GitHub repo. So you just grab it from the repo by running the kubectl create file, and then you put the URL for it, and it grabs the code and then installs it on your Kubernetes cluster. So what we are going to do is actually the first thing before applying any policy is that we need to check if it is going to work. So what this is going to do is that it's simulating a request to the service. So like if you paste it here, this is the X-wing. Before any type of policy, it just says ship landed. Okay. If we take the other one, the TIE fighter, again, apply it here, it should say the ship landed. Okay. So yeah, so the next step is to actually block level 4 type of traffic. So what to do that? What we'll do is that we'll need to grab the network policy here, and it's again on a GitHub repo. And of course, we need to pray for the demo gods that it would work. Crossed. Okay, so now the policy is working. The TIE fighter should say ship landed. the X-Wing guy should time out. Yeah, so that's good. It's going to take a while to time out, so I'll stop it. But basically what that means is that because the the X-Wing, if we go back to the slides maybe. Yeah, so because, where is it? This guy. So because this guy is using the org alliance, so it does not match, it's not allowed to talk to the org empire. So because the policy was, so this is the policy that I just applied. The policy is saying if the traffic coming in to the service Death Star from an org empire on port 80, suite as allow. Anything else is implicitly denied. Okay. The next step is we need to now apply this policy, which is to not only block TCP traffic coming in from any other source beside the org alliance, even within the org empire, if the traffic is going to anywhere else beside request landing, exhaust port or whatever, it's going to fail. Okay. So for that, we need to apply this policy, which is basically, again, exact simple policy, but with only one addition, is that another rule saying if anything beside a post to this path, anything is to this path is allowed, anything else should be denied. So fingers crossed again that this should work. All right, so this is the policy here. And as you can see, it's still trying to do something, so it's timing out. So we now pulled in the next policy, the layer 7 policy, again from the GitHub repo, and it says configured. So the first, this one, the TIE fighter, because it's going to request landing, nothing changed, should say ship landed. The X-Wing should still be denied. Okay. Yeah, it's denied, it's going to time out. The last thing that we want to try is to use the TIE fighter, which was allowed to talk to request landing, but now the code should say exhaust port. Okay, so this is basically not explicitly allowed, so it's implicitly denied. So what's going to happen here, and fingers crossed it works, X is denied. Woohoo! Yeah, so that's basically it. That's the whole demo. And thank you, everyone, and I hope you find this useful. And again, you could find me on Twitter, and I've got my own blog. And yeah, thanks so much. Appreciate it.